Okay. The spread of disease project, people typically end up doing with zombies because I guess zombies are still cool. So let me give you an overview. These projects are always different. Everybody takes a different approach with this particular project. All the other projects, the Skydiver project, like I literally laid out, you're doing exactly this. There's not much wiggle room. This project, though, there's a whole lot of wiggle room. So the typical project people will do is what are called the SIR type models to begin with. So let me show you what those are. And yes, I went to Wikipedia. If I'm learning a new kind of math or physics, Wikipedia is my first resource. There are mistakes. In fact, there used to be mistakes in this page, but they've been fixed now. But it's still a good resource. So the SIR model is a system of differential equations that's coupled and nonlinear. So S here is the number of susceptible people at time t, I is the number of infected at time t, and R is the number that have recovered at time t. And we could see a flow diagram here. Everybody starts susceptible. Well, you start with a couple people infected, and then you flow out by this amount, you're flowing into infected. Notice the people that are flowing out of susceptible are the same people flowing into infected. And then, see, remember, these are derivatives. So my derivative is negative because S is decreasing. My derivative is positive because that decrease from here is going into here. But then there's this negative term. People are flowing out of infected into recovered. Like I said, this is a system of nonlinear DEs. We don't know how to solve this. This project is different. You're not going to be solving any differential equations. The purpose of this project is more, think of it more like a book report. You're just giving a whole bunch of information. You won't be doing any math yourself. You're giving a bunch of information about a bunch of different models. And again, the way people typically do this project, to make it cool, they do it in terms of zombies instead of just a random infection. If you choose this project, though, for project two, you're going to have to learn a little bit of MATLAB coding. I'm going to teach you a little bit of how to code in MATLAB to produce graphs like this to model this situation. So if you're interested in a little bit of coding, you could do this in Excel. You could do it in Python. If you know Python, it's not hard to code this up in Python. I already have some MATLAB, the free version, Octave scripts already written that you'll be modifying in project two to produce some graphs if you choose this project. You could also do those same things, like I said, in Python or C or whatever. Okay, so this is the most basic model. It's called SIR. We could take that model up a step by throwing in another category. In SIR, everybody recovers eventually. The next level up is SIRD, where now you throw in this extra category where people die. And you get pictures that look like this. This may look familiar to you. Over the past few years, we saw similar looking pictures for COVID. That's really what we're talking about here. Sure, we're going to talk about this in terms of zombies, but we're talking about COVID. We're talking about the spread of a disease through a population. Remember talking about flattening the curve a few years ago? This is the curve we were trying to flatten, the infection curve. We were trying to flatten that curve by lowering this number right here, our beta. Remember we were talking about R naught values? That's related to beta. So we got the SIR model, the SIRD, the SERV, where now we have a vaccine. And like in this particular Wikipedia page, they're assuming not only have we thrown in another variable, but all of my parameters could also be functions of time. Maybe beta is not a constant. Maybe beta changes with time. And look at this cool little animation they produced here. Look, they're lowering beta, they're flattening the curve. Then we've got the served model, where again, they're assuming here. I don't like, see, again, I think Wikipedia is a great place to learn about something, but it's not always the best source. Somebody different wrote this up because now they've changed the variables. And they've also changed what these variables mean. Notice up here we're always divided by n, and now we're not. That's because that's been incorporated in here. So this isn't perfect. I'm not saying it's perfect, but it's good enough for me to explain to you what the project is. So here's the next model, served. We could also throw in, like, honestly, this is new. I've never even seen this before. I don't even know what beta is. Oh, it's not another variable. It's just we changed what happened here in this equation. And you can see there are a bunch of different models here. So if you take this project, what you would basically be doing is explaining several of these models. That would be, say, part one. Explain several of these models. Show some pictures that you're probably going to have to steal here from Wikipedia or other sources. Like you'll have this picture on the screen during your presentation. You'll talk about, look, we can see here that the maximum infection here with these particular parameters occurred after about 22 days, and it was about 700 people were infected. If we were to lower beta, this would have gone down, that kind of thing. So again, it's just more information dumping than actually doing any math. But you would do everything, if you choose, in terms of zombies. So when you type all this up, a lot of groups, instead of using the letter I here, like to use the letter Z for zombie. I think it's perfectly fine to just keep it I, then you can use their pictures. But a lot of groups like to use Z. Okay, so part one, explain, let's say, at least three different SIR type models. So probably SIR, SIRD, served, where we throw in the V for vaccination. And when I say explain, I mean you're going to have to type all this up. You can't copy anybody else's math. You're responsible for your own math. Type all this math up. Explain what all these parameters mean. Maybe include a flow chart like this. If you steal somebody else's image, you have to give them credit. Like I can, copy this image, but then right underneath it in the paper, I need to put where I got it from. I can copy this image, but put where you got it from. Explain what all these parameters mean. Show some graphs and explain what we see going on here. Write a couple of sentences about each graph. That would be part one. Then there are a lot of other ways we could model outbreaks. So I could just Google here like it just popped right up, differential equations, and look at all the other ways people are modeling zombies. This paper is doing it in a diffusion model. Now, this does involve partial differential equations, but it's still something you could present to the class. Hey, here's a way people are modeling zombies. as you know, they start, all the zombies are in one place and they spread out. Like if you put a drop of food coloring in water and it diffuses throughout the water. It's a diffusion model. And this is called the diffusion equation. So you could basically reproduce the information here from this paper. Now, of course, you wouldn't want to go into all the really deep detail, just a broad overview of what's in this paper. Here's a different paper on zombies. Because zombies are cool, so people for the last few years have been using zombies to explain math. This is the SIR model. I mean, the parameters look a little different from what we saw on Wikipedia, but that's what this is. It's the SIR model, only now they're calling it Z instead of I. And here's a nice flow chart. So if you want to do it with zombies and you want to use Z, you could steal this flow chart. You just got to be consistent. Make sure your equations match what's shown. And another way we can model predator prey. The Lotka-Volterra model. Is this the one I was just on? Yeah, it was. Let me pause and find it for you. There's a good paper out there. Okay, here's a source. I'll show you how I got here. I just Googled predator prey zombies. You could watch this video, learn about predator prey models for zombies. I don't think this makes a very good zombie model, and I'll explain why when I explain Lotka-Volterra. I'm just saying this is an option if you want to include something else as another model we could use to model zombies moving throughout a population. So to get there, I Googled that and I came down to here. Okay, now what is Lotka-Volterra? It's another system of a couple of differential equations where X represents my prey, say rabbits, and Y represents the number of foxes, my predators. So the foxes are eating the rabbits. And I've got some regular population growth term here. So the more rabbits I have, the faster rabbits are going to repopulate. Like if I took out this term, that's just regular old population exponential growth. Remember, these are derivatives. So the rate of change of rabbits is proportional to the number of rabbits. It's like the very first model we ever looked at in the first week of class. It's a positive because my rabbits are increasing. But then we take away here this term that depends on the number of foxes. So if I have foxes, they're eating the rabbits, it's going to decrease a negative derivative, my number of rabbits. Then over here in this basic, this is the most basic of the Lotka-Volterra systems. If I have too many foxes, they're competing for food. That's why there's this negative term here. But if I've got a lot of rabbits, I've got plenty of food. And we end up with graphs that look like this. So I've got my prey and say they're increasing. That means there's more food for the foxes, so they'll start increasing. But now I've got too many foxes. They're eating up all the rabbits. So the rabbits start to die off. Now there's a delayed reaction. The foxes don't have enough food, so they start to die off. Oh, well, now the rabbits will start making a comeback because they're not being attacked by the foxes and so forth. So you get this cyclical type behavior in this most basic model. We could even graph what's called a phase diagram here, where we're looking at foxes versus rabbits. Here, this was fox and rabbit versus time, both on the same picture. Now it's foxes versus rabbits. So here, say number of rabbits are going up, well, then number of foxes are going to be going up. My Y's are increasing. Now I've got too many foxes, so my rabbits start dying off until I reach this point. Now there's not enough food, so now the foxes will start dying off. We go around these cycles counterclockwise. These can be bumped up. They're more advanced versions of Vodka Volterra. In a Vodka Volterra system, we can find fixed points. That's what's going on here, where both systems equal 0. So if dx dt and dy dt both equal 0, then both of these equal 0. We could solve x and y in terms of alpha, beta, gamma, and delta here. And we get this fixed point. It's in here somewhere. Right here. Say these would be my two fixed points. Both start at 0. Or if I start with these exact numbers, these are equilibrium points, both species would just maintain a constant pollution or population. Of course, it's not very realistic. There are more advanced models out there. So we could do the same thing in terms of zombies and humans. I don't think it makes a very realistic model to do this in terms of zombies, though, because zombies are turning humans into other zombies. They're not just eating the humans, right? So it's not perfect. When you kill off a human, they become a new zombie. They're not just food for the zombies, which this model assumes. But if you're looking for extra material to put in there, you can do this. Again, this project has a lot of leeway. Then, once you got all this, absolutely, this part is required. We're not really talking about zombies. We're talking about the spread of disease. So at the end, let me put all this here. So one, explain at least 3 of the SIR models. Then two, do other types of models. So that could be that diffusion one I showed you. Diffusion or predator prey, Lotka, Volterra. Or you could Google and maybe find somebody that's tried something different. Do some more stuff. Remember, your whole presentation is going to be 10 to 15 minutes long. So if you do a whole lot here, maybe you do 5 or 6 different SIR type models, you might not have time to do more here. I've had groups that did everything up here and it turned out to be a fantastic project. I've had other groups that just barely skimmed the surface here and spent more time in here. It's totally up to you. This project has more leeway than any of the others. But no matter what, bring this all back to COVID. These SIR type models. That's what we're really talking about. So in any of these, you're going to type up all your math. You're probably going to have to steal graphs and images from other people. Make sure you cite your sources. Make sure you're consistent. If you're showing an image that is using certain letters, you need to be using the same letters in your paper and in your write-up about that. And now COVID. Say surge. You can find a lot of stuff out here about how these models were actually used to model COVID over the last few years. Again, you're going to do some research, you're going to read some papers, Find some graphs that you understand. Make if you don't even understand the graph you're looking at, don't put it in your paper. But do some research here, find some actual graphs of COVID infection, put it in your paper and talk about those graphs. We could see here that they were using the served model. Here, let's just pick one. I'm trying to find a picture here. It looks like we're measuring R naught values there. I think this is a graph just for I. So this is what the model was predicting. Those were the actual values. And we talked about flattening the curve. That's what we were talking about. Now you'll have to read a little bit to see exactly what's going on here. And there are hundreds of these papers out there. Find some, relate everything you've talked about here in terms of these spread of disease models, these guys here in terms of COVID. You can't always get full PDF here on just by Googling. You can go to Google Scholar, and a lot of times you'll find the full article or paper in Google Scholar. If you can't find what you're looking for there, sometimes it'll just be the abstract. You can go to the Valencia website. You can go to MyVC and go through the library. So let me show you how to do that. They've just changed everything. So I may have to figure this out myself. In fact, let me pause while I figure it out. Okay, this should get us here so you can see where I've gone here. And we should be able to go to databases. They've just updated all this, so I'm figuring out on my own. And academic search complete. Like you probably learned all this back in high school. And I can just look up COVID surge. Or I could look up, say that I found an article and I couldn't get the full PDF. I could type in the name of the article here. And I can find it here and probably download the. I don't want just the abstract. I want to make sure it says full PDF on here somewhere. I'm not sure if this one has full PDF there. Okay, and then again for project two, whatever you choose to do in project one, we are going to numerically calculate what the graphs look like. We're going to produce graphs numerically using what's called Euler's method. So you're going to have to learn a little bit of coding to do that. Project one is really easy. It's the easiest of all the project ones. And it also has the most freedom. Okay, that's a good place to stop.